for A. In this case, we're trying to find the asymptotes of x squared plus 6, all divided by 3x squared plus 7x plus 2. Let's start with the vertical asymptotes. Where do I find my vertical asymptotes? The denominator. What about the denominator? The zeros of the denominator. So we want to know when is, go ahead and set this up. When is this 3x squared plus 7x plus 2 equal to 0? All right, a little bit of factoring, or you could always use the quadratic formula here. That would also be totally fine. But I like the factoring. It'll make a point later on. What does this factor into? Factor into 3x plus 1 times x plus 2. And so what are my vertical asymptotes here? And don't forget, it's always x equals negative 1/3 and x equals negative 2, because technically what we are referring to is the vertical line at the x value of negative 2 and the vertical line at the x value of negative 1/3. All right. And then for our horizontal asymptote, what are we looking at? What's kind of the question that we ask? Yeah, what numbers matter as x gets really, really big in either the positive or negative direction? So at very, very, very large values of x, looking at our numerator, what kind of disappears? What kind of stops mattering? Looking at the numerator, that plus 6 really doesn't have much of an impact. If we're thinking about the difference between like 1,000,000 and 1,000,006, as x gets really, really big, we notice that plus 6 less and less and less and less and less. And so as x goes towards positive or negative infinity, this numerator really kind of goes to x squared. Or that's kind of the loose way that we are thinking about it for now. And then looking at our denominator at very, 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 very large values of x, again, kind of thinking like our end behavior here, what's going to stop mattering? So definitely, I think the 2, but then what else is going to stop mattering as well? Also that 7x. And so all we are going to look at is really the leading term of each the numerator and denominator dividing by each other. What is this going to be equal to? 1/3. And so for my horizontal asymptote, I get the equation y is equal to 1/3. Again, that horizontal line, y is equal to 1/3. We're actually going to adjust this process ever so slightly. We'll see C is going to throw a little bit of a wrench in that plan for how we do this. But for now, this is a pretty good kind of representation of what we will do, what we're doing. All right, let's take a look at B here. B threw a little bit of a kind of tricky bit here. So x plus 6 over the exact same thing, 3x squared plus 7x plus 2, not plus 6. Have we changed our denominator at all? No, so we'll just go ahead and assume that our vertical asymptotes are going to be the same. X equals negative 2, x equals negative 1/3. What's going on with our horizontal asymptote? If we do the exact same check here, what happens to our numerator as x goes to either positive or negative infinity? What stops mattering? In the numerator, what stops mattering? The plus 6 stops mattering, so we're just going to focus on the x. And in my denominator, what stops mattering? Still the 7x plus 2. And so again, just focusing on this 3x squared. What is this going to simplify down to? 1 over 3x. Now, this is not the equation to a horizontal line. Right? This is like one of those weird rational functions that we looked at. But we have to keep in mind that this is only the case as x is getting really, 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 really large. So we can continue to kind of make observations here. As x gets really, 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 really large, what happens to 1 divided by 3 times a really, really large number? 1 over really, 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 really large becomes or starts to approach what? 0. This goes to 0. And so what is our horizontal asymptote? That is going to be the line y equals 0. All right, one more here. This is x squared plus 6 times x plus 2, all divided by 3x squared plus 7x plus 2. Vertical asymptotes, have I changed my denominator at all? No, so we'll just go ahead and assume, we'll see, erroneously assume that our vertical asymptotes are the same. But for now, this is good enough. X is equal to -2. X is equal to -1/3. And for our horizontal asymptote, looking at the numerator, when we do out all of this kind of multiplication, what is that leading term going to be? X cubed, very good. We're going to end up with an x cubed on top, and then what are we going to end up with on the bottom? Still a 3x squared. What does this simplify down to? X over 3. And again, what is happening to x here? This is as x is getting very, 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 very large. A very, 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 very large number divided by 3 is still going to be a very, 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 very large number. Does this equation settle down at a particular value? It does not settle down. And so we would say that the horizontal asymptote does not exist in this case. Okay. A couple of things that I would like to observe here. First of all, the way that I just described the horizontal asymptote as a value that we are settling down to is not how I described it on Friday. Right? On Friday, I said, well, really, we're not settling down at a particular value. We're really approximating a function. Right? We are approximating the function y is equal to 0 or y is equal to 1/3. And so why wouldn't we continue that trend even when we see that this kind of approximation doesn't settle us down to a value? We're going to see that, in fact, we do continue that trend. It's just called something different because we're no longer going to be a horizontal line. And then the other question is actually one that we don't even really know to ask, but hopefully is one that we can see when we look at the graph of this function. So taking a look here, this is our graph of example A. Just as far as like relevant behavior is concerned, just to kind of visualize what is going on, these are our horizontal asymptotes that we have here. All right. Notice that as our function approaches each of these asymptotes, so for instance, as we get really, really close to -1/3, we see this explosive behavior that we defined as kind of creating our asymptote, where our function, as we get really close, shoots up towards positive or negative infinity. Likewise, around that 0 of -2, we see that explosive behavior of shooting up towards positive or negative infinity. And as we zoom out, what does our function start to really look like? It's just a straight horizontal line. It looks like it might be at 0. In fact, that's just how zoomed out we are. It would be at 1/3. But just kind of like, again, we could like zoom in at any particular point and we would say, yeah, it's converging to 1/3. It's going to be kind of approaching that value of 1/3. But again, really the idea is we are approaching the function y equals 1/3, that our function is doing a better and better job at acting like that for larger and larger and larger values of x. All right, let's compare this to what we get from C. So first of all, from C, just kind of this initial observation here, I'm going to turn these off for now while we talk about it, is that we ended up with not having a horizontal asymptote, but I still kind of want to ask that question, what happens when we zoom out? What happens at particularly large values of x? And as we zoom out, what does our function start to pretend to do? What is it acting like? It's acting still like a line. It's just not a straight horizontal line. It is a slanting line, right? It would be a line with a slope that isn't just 0. This would just be a line with a slope. If we had to guess the slope of our line from what we looked at when we were trying to figure out if there was a horizontal asymptote, does anyone have a guess for what the slope of that line that we saw, a guess for what that would be? 1/3 would be a really, really good guess. And in fact, what we are going to see is that if we use y equals, this is x over 3, but you could think of this as 1/3 times x, then notice that our red line almost completely overlaps what our function becomes. It doesn't actually overlap. If you were to, again, zoom in at any particular point, you might have to zoom in a lot, but eventually you would see that, yeah, there is in fact a little bit of a gap between our function in blue and that line, that 1/3 x line, and that would persist, but that gap would get smaller and smaller and smaller as x gets larger and larger and larger. And so rather than approaching a horizontal line, we instead see that for large values of x, our function approaches a slanting line, or a line with a slope that isn't 0. So exact same idea as horizontal asymptotes. It's just that the function that we are approaching isn't a linear function. It is instead, it is a linear function. It's just not a horizontal linear function. It's not a constant function. It's a linear function. This is not special behavior to lines. In fact, you could see this behavior for any type of function. The reason why we see a linear function here is because we have a 3rd degree polynomial divided by a 2nd degree polynomial. If I were to add a root to this polynomial, for instance, let's say I add, let's throw in x minus 1 here. We'll turn this off. We get all sorts of craziness going on locally at kind of those small values of x, but what is this going to look like as I zoom out? What does it start to look like? We got a whole bunch of craziness when we're zoomed in. Who knows what on earth is going on here? That's so wild. And then we zoom out, and what does our function look like the more and more and more and more that we zoom out? It looks like x squared. It looks like a quadratic function. And you could get this with a cubic function, and you could get this with a 4th degree function. You can get all sorts of this asymptotic-like behavior. It is not exclusive to lines, but we are going to be focusing on this kind of slanty line business as far as our asymptotes are concerned. Just to kind of keep in mind that, again, this is a function that we are approximating. It could be anything. It could be x squared, it could be x cubed, who even knows? What we are looking at specifically as far as our definitions are concerned are slant asymptotes, which are basically just horizontal asymptotes, except they form a slanted line instead of a horizontal line. I'm going to call them horizontal-esque asymptotes. Except we approach a slanted line rather than a horizontal line. And we could look at, again, quadratic asymptotes and cubic asymptotes and all of that, and that would absolutely not be an issue. And we'd use the exact same tools. As x gets really, really big, what is happening to our function? Now, a little piece of intrigue here is that the line 1/3 x does do a pretty good job of what our function is tracking, right? If I were to go back through, let's delete this 0 here. Whoop, that is not what I wanted to do. That's fine. This was what, x plus 2. Cool. If I were to say go back here and look at this. If I were to go back, 1/3 x does a pretty good job of following our function, but we lose a little bit of specificity here. In particular, when we've done this, when we've kind of only looked at the first term of our numerator and the first term of our denominator and used that to determine what is going on, we get a really, really accurate view of what the slope of our slant asymptote is going to be. We get a much less accurate view of what the y-intercept of that slant asymptote is going to be. So we do lose a little bit of information with this kind of shortcutted way of what we've been doing of looking at the horizontal asymptote. We can adjust for that, though. And in fact, that's what we're going to look at here is when we are actually taking the slant asymptote, it's generally not sufficient to just ignore what's going on in our function. We have to do a little bit more to kind of get that detail that we need. You need to do the same thing for a quadratic asymptote, for a cubic asymptote, all of that fun stuff. So let's take a look here at example 2. We are trying to find the slant asymptotes of the given functions here. In particular, I want to look at 2b because that one is the slightly more complicated one of these two examples. Normally, if we were treating this exactly like with a quadratic, with a horizontal asymptote, we would just say as x gets really, really big in my numerator, what stops mattering? The -12. As x gets really, really big in my denominator, what stops mattering? The +1. And so we would say, this is going to look like 6x squared over 2x. And so this is going to look a whole lot like 3x. And we could certainly try that. Right? So we could think of taking this as, we'll say like y equals what, 6x minus 12 divided by 6x squared minus 12 divided by 2x plus 1. And yeah, as we zoom out, we get, oh yeah, that's going to be a line with a slope of 3. That's all cool. And we could try y equals 3x. And again, it does a pretty decent job, but it doesn't do a great job. There's always this gap here. And when you zoom in, the gap doesn't actually get super small. So again, this does, when you zoom out, a pretty good job, but there's always a fair bit of error. And actually, we can minimize that even more if we can find what the y-intercept should be that would better match to this function. So that's kind of our goal here. We found the slope. 3x is kind of our nice cheaty way of doing it, but this doesn't actually do a super good job of telling us what our function is pretending to be. We need to be a little bit more refined than that. So to be more refined than that, we're being asked to divide a polynomial by a polynomial. We know how to do that. We can actually do out that long division. Let's see what this gives us. So this is taking 2x plus 1, dividing it into our 6x squared. What do I have to remember to include? Plus 0x minus 12. Very good. How do I match 2x to 6x squared? 3x. Very good. That's the 3x that we saw before. as ignoring, if we just look at the front term, just look at the back term, or the bottom front term. So this is going to give us a 6x squared plus 3x. Subtracting the two, what's 0x minus 3x? Negative 3x. And then how do I match 2x to negative 3x? In this case, think what number do I need to multiply by to turn 2 into a negative 3? 3 over 2. I'm trying to cancel a 2. I'm trying to leave behind a 3. So I want to have, and I'm trying to make it negative. So I need a negative 3 over 2 here. So a little bit of a tricky one. But that will give us a negative 3x minus 3 over 2. We are subtracting these two. And I get like negative 10.5 here. What is this negative 10.5? That's my remainder. Think of this as being like what's stopping my function from actually being 3x minus 3 over 2, right? The fact that I have a little bit left over here means that this 2x plus 1 does not divide evenly into this function. It does not fully become. It's a little bit of error. And we've had a couple of different ways that we could write this error. The way that we're going to do it here is we're going to do it with the like plus the remainder over the thing that we're dividing by. Remember doing this when we were doing the long division? Okay. Now, ultimately, our slant asymptote asks the question, what happens when x gets really, really big? And to that end, my question is, what happens to this as x gets really, really, really big? Negative 10 divided by some kind of expression of x as x gets really, really big. Constant divided by x is going to go to 0. And so this error bit, this remainder, is going to become less and less and less relevant. Our function is going to converge to this 3x minus 3 over 2. 3x was not a bad guess. 3x gets us pretty close. We're missing a little bit of specificity, though. Look how much better when we subtract 3 over 2. Look how much better our line does at getting really, really close. That is significantly, significantly better. That is significantly less error when we include that y-intercept. Okay, so slant asymptotes. Whenever we do this kind of comparison, I had a student in my last class ask a really good question, which was, how do I know whether I can just do this kind of shortcut of just comparing first term to first term, or whether I need to do out this long division? If when you do my comparison of looking at the first term divided by first term, and you end up with an x in the numerator, that is a clue to you that, oh, there's information that I'm losing here. I need to actually do out this division to see what the full picture is, what the actual function is that I'm approaching. If there is not an x in the numerator, if my x's fully cancel, or I end up with constant divided by some kind of expression of x, then we know that's just going to be a horizontal asymptote. That's going to settle down at a particular value, or it's going to settle down at 0. It's either going to settle down to the ratio or settle down to 0. I don't need to do the long division. You certainly could, and when you do the long division, you'll get the same answer for your horizontal asymptote. The remainder bit will go to 0, and you'll end up with the exact same thing, but you certainly do not need to. All right, questions about slant asymptotes? Yes, Sadie. Sure. So slant asymptotes, just like horizontal asymptotes, these are the functions that we approach as x gets really, 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 really big. Except the difference now is that rather than our function being a constant function, it is now a linear function. And absolutely, we could have a quadratic asymptote and it would be the exact same thing. And absolutely, we could have a cubic asymptote and it would be the exact same thing. Same idea of what is going on when x gets really, really big. In this case, in the case of slant asymptotes, that's if we mimic a line or if we approach a line. I think last time we phrased it as if we pretend to be a line. I think Dylan had the question of who spends their life talking about functions that pretend to be other functions. And again, we're kind of condensing that. We're providing some terms to help us understand the gist of what is going on without applying a whole bunch of excessive mathematical rigor to it. Because that would be an analysis course where you apply all that mathematical rigor to it, and that is not what this is. All right, so that was one of the things that was different about C. That was kind of the thing that we noticed right off the bat that was different about C, was we don't settle down at a particular value. We have this weird asymptote that's a function of x, and it's not a function of x that's going towards 0. It's just a function of x. And now we're saying that's okay. That's fine, and we can get a very precise look as to what that function is with long division, where we then ignore the remainder. But that is not all that was going on that was weird with our function here. So that was part of it, not all of it, though. Okay, so this was C. And these were our asymptotes for A. And we said that they're the same. The zeros of our denominator haven't changed. And in fact, we still see one of the original asymptotes here. Which asymptote do we still have? Where is our function still exploding towards positive or negative infinity? Say again? Not 0. Which of these two lines? So we looked at these two asymptotes before. As we approach one of these two lines now, before when we approached both of them, we saw that kind of like explosive, like shooting up and down effect. And now we don't around both. Which one still has that asymptotic behavior? Where does our function? Say again? So looking at my purple or green line, which of those, when we approach that line, causes our function to kind of fracture apart and explode? The green line, our function is breaking apart around the green line, shooting up towards positive negative infinity? No, remember what we looked at before did have that happen. So this is just kind of a reminder here. This is what our function was doing before. Notice that around that green line, my function is shooting up towards positive negative infinity. It is going towards very, very large values as I get really, really close to that 0 of my denominator, that -2, 0. I see the exact same effect, or at the very least a very, very similar effect, around that -1/3, 0. But what happens when I add this x plus 2 root to my numerator? I still see that explosive effect around 3x plus 1. Where do I no longer see it? Okay, I need everyone to take a moment to put up their laptops, because I really don't want to have to answer questions about like, oh, why are these things different, when I'm like really trying to, guide us towards understanding the answer ourselves. Okay. Let me rework here. The denominator of our function here. We already did this factoring. All right, we said that this was the same as 3x plus 1 and x plus 2. And our claim was, well, we see vertical asymptotes around the, remember our definition before, around the unchecked zeros of our denominator. And then I proceeded to not explain what that means, what that unchecked word is there for. But we see them around the unchecked zeros of our denominators. When is our denominator equal to 0? Well, our denominator is equal to 0 at, because of this 3x plus 1 root, negative 1 over 3, and because of this x plus 2 root at negative 2. Okay, so now looking at the graph of my function, those were my zeros before. Those are my zeros of my denominator, negative 2 and negative 1 over 3. Where do I see asymptotic behavior? Negative 1/3, not negative 3. Still at negative 1/3. All right, so our 3x plus 1 root is still doing what it does. That's still, as x gets really, really close to negative 1/3, that is still making our function kind of explode in the positive or negative direction. Why do we not see the same thing around negative 2? What is happening to the x plus 2 root in my denominator that is not allowing it to govern the behavior of my function like this 3x plus 1 root? Why can this x plus 2 root in my denominator not control what my function is doing? What's happening to it? Say again? So it's not increased. So as we're getting really, really close to negative 2, x plus 2 gets really small. So our denominator is getting really, really small. Why do we not see that in the graph? What is preventing us from seeing this explosive effect of numerator staying the same and denominator getting really, really small? Why don't we see that as we approach negative 2? Say it again. One more time. Because x plus 2 is in our numerator as well. What is that causing to happen to the x plus 2 in our denominator? They are canceling each other out. Our denominator is getting really, really small. Just like around negative 1/3, our denominator is getting really, 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 really small. But what else is getting really, 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 really small? Our numerator is as well. What this x plus 2 in our denominator does is countered by this x plus 2, is kept in check by this x plus 2 in our numerator at almost every single step along the way. And so we don't end up with an asymptote. We don't see our function shoot up towards positive or negative infinity. That explosive behavior is curbed by the fact that it's canceling out with the x plus 2 in our numerator. Yeah. Yeah. Exactly. Exactly. Almost all the time. What is the one value where these don't actually cancel? So x plus 2 divided by x plus 2 is 1 and cancels everywhere except for one value of x. Say again? So negative 1/3 is still going to be fine. You'd end up with negative 1/3 plus 2, which is going to be like 5/3 divided by 5/3. Still going to be 1. That's still okay. Negative 2 is still going to be an issue, though. Right? So all of those numbers getting really close to negative 2, totally fine. Totally, totally happy. All right? But right at negative 2, we see an issue, which is that I end up with 0 divided by 0. All right, plug -2 into this function, you'll end up with 10 times 0 over what? -4 times 0. That's 0 over 0. Actually, I think whatever, I did my math a little bit wrong there. No, I didn't. And so only at the 0 do we have this issue. You actually don't see that in this picture. You're going to have to kind of take my word. This issue is, in fact, here on this picture. You just have to zoom in like so infinitely small to be able to actually see the little skip that you would have. But essentially what this would look like and the way we would communicate that is our function is basically going to be ignoring that x plus 2 entirely, except when we hit -2, and then it's going to skip that point and then continue ignoring that x plus 2. So there's this tiny, tiny, tiny little gap that only exists at that particular 0. What we see there is a hole in our function. So a hole here is a point that is removed around, or maybe at is better than around, at a, and I'm going to again use this word, at a checked 0 of our denominator, where now we know what it means to be checked. What does it mean for a 0 to be checked here? Why is x plus 2 kept in check, whereas 3x plus 1 is not? Because we see the same factor in our numerator. So keeping a factor in check means you see the exact same factor in the numerator as well. And that creates not an asymptote where we get big explosion, that instead creates a hole where we basically ignore that x plus 2 is there until we hit -2, and then we have to skip over -2, and then we keep going, pretending like it's not even there. Yeah, Sadie. So unchecked is the one that explodes. So the unchecked is like this 3x plus 1. There is nothing stopping this 3x plus 1 from just controlling that function around that -1/3. Right? There's nothing to prevent when that gets really, really, really small, us from having number divided by really, 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 really small. We see that explosion towards positive or negative infinity. Keeping something in check. So like this x plus 2 in our numerator prevents the x plus 2 in the denominator from having that crazy, crazy explosive behavior. It keeps it in line. It keeps it in check. That's not a technical term. That's not a math term. That's just how I am kind of using to, again, casually describe what we are seeing. The x plus 2 in our numerator prevents the x plus 2 in our denominator from doing whatever it wants. And so you don't see a vertical asymptote here. Instead, you just get a little skip in your function. Yeah, done. Sure. So it is a point that is removed at a checked, again, just like where we see the same factor in the numerator and denominator, at a checked 0 of our denominator. Which is, again, not a math term. If you use that with any math teacher or math professor outside of this classroom, they're going to look at you like you're crazy, or maybe not. Maybe they'll understand exactly what you're saying. This is just to kind of keep us here kind of focusing on these zeros in our denominator are causing this erratic behavior to happen. And so it's only when we see them kind of counterbalanced by what's going on in the numerator that they are not allowed to just run away with the function and do whatever they want. They don't get to create that vertical asymptote that they're like trying to create. Okay, let's take a look at a couple examples here, and then hopefully it'll make a little bit more sense. So example 3, kind of trying to do everything at once with our rational functions. So we are trying to find the asymptotes. These could be slant asymptotes. They could be horizontal. They could be vertical. Who knows? We are also trying to find the holes of our particular equation here. So now we have, again, we can kind of start with vertical asymptotes, but now we also need to check for holes. So still need to factor my denominator to find the zeros, but now what else do I need to factor? I got to factor the numerator as well to see are any of them kind of being kept in line. Okay, so looking at A here, what is my numerator going to factor to? X, I think X minus 2. Yeah, X minus 2 and X plus 3. Two numbers that multiply to make -6, add to make 1, -2, and +3. And then for our denominator, this is a special case, the a squared minus b squared. We looked at this a little bit before, difference of two squares. But the way that we could approach it, kind of that regular factoring way, what are two numbers that multiply to make -9 that add to make 0? 3 and -3. And so we'll see exactly that as well. And so where do we have the zeros of our denominator here? So -3 and 3 are the zeros of our denominator. Which one is going to represent a hole and which one is going to represent a, let's start with, which one's going to be a vertical asymptote? 3 is going to be a vertical asymptote coming from this root right here, which notice is not kept in check. There is nothing in our numerator to prevent that x minus 3 from running wild when we get really, really close to 3. On the flip side, what's happening around my -3, 0? We see the exact same thing in the numerator. And so rather than a vertical asymptote, I'm going to have a hole at x equals -3. Okay, so vertical asymptote was our straight up and down line. A hole is not a line, though. What is a hole? It's a point. It's a point that we've removed from our graph. I have here the x value of that point. What am I missing? The y value of that point. Okay, so this can be something that I think people find a little bit tricky conceptually. That's fair. If we wanted to really get into why we can do this, we'd have to have a calculus lesson, and I'm not interested. Well, I am interested, but I'm not going to make you go through a calculus lesson to kind of get at this math. Again, we're going to kind of keep this in the gist of what we are doing. So we're looking for a y value. Essentially, we're looking for the y value that our function skips over as we kind of move through this value. In other words, we kind of want to know what the y value of our function was supposed to be if we were allowed to plug -3 into our function. So we're not allowed to plug -3 into our function. That gives us a 0 in the denominator. But we can make the observation that everywhere else except for -3, what's going to happen with my x plus 3 divided by x plus 3? What are they going to do? They're going to cancel everywhere except for -3. And so what our function looks like is this f of x really is x minus 2 over x minus 3, except when x is equal to -3. They cancel everywhere except that one value of x. And so if we want to figure out what the value of y should be for this particular function, well, let's try plugging -3 into our function and see what that tells us. All right. So we plug in -3, noticing we observe we can't actually plug -3 into our function. We'd get a 0 in the denominator, but we're going to say if I was allowed to plug -3 into this function, what would it look like? This is going to be -3 minus 2 over negative 3 minus 3, I get negative 5 over negative 6, or 5 over 6. So if I were allowed to plug negative 3 into my simplified function, which I cannot, I would get an output of 5 over 6. That tells us the y value for our whole. And so our whole is the point 3, 5 over 6. Again, calculus. So what that means of like what it's supposed to be has a very technical definition that we're not going to get into, but that's kind of the gist. Is you say, well, I'm going to cancel it. It cancels everywhere except for at this hole. And what would it be if it were allowed to kind of be at this hole? It's going to be that, in this case, 5 over 6. Yeah, Dylan. So the root that is repeated is x plus 3, but the 0 that is repeated is negative 3. So it's the 0 that accompanies the root that we see. All right, cool. Looking at this particular function, we've got one more thing that we have to check for, horizontal or slant or quadratic or cubic, whatever, asymptotes as well. So what happens as x gets really, really large? Let's do our cheaty check and then see if we can avoid needing to do that long division if we don't have to. As x gets really, really large, what is the only thing that continues to really matter in my numerator? X squared. What's the only thing that really continues to matter in my denominator? X squared over x squared is just 1. Do I have any x's in my numerator left over? No, that's fine. That's just going to be my horizontal asymptote. All right, questions here with 3a. All right, let's take a look at 3b as well. Honestly, what I would do, ultimately what you will need for these questions is you will need both the factored and the unfactored form. So we're given the unfactored form. If right off the bat you wanted to factor that numerator just to kind of get a scope of what things are going to look like, that would not be a bad idea. But what I want to do is kind of approach this one a little bit backwards so that if you didn't do that, how could you kind of interpret the results that you get and still be able to move forward if they kind of got a little bit different looking than what we've seen up until this point. And so normally we've been starting with the question of vertical asymptote and now whole. I'm going to start now with the opposite, what's going on as x gets really, really big. Again, we're going to kind of see that that's a little bit of a backwards approach to what we should be doing, but that's fine. We'll resolve that as we go. So looking at this function, if I'm asking the question, what happens as x gets really, really big, what do I kind of really only care about for my numerator, at least for now? 2x squared, what do I really only care about for my denominator? An x, what does that simplify down to? 2x, do I have an x in my numerator still? Yes, and so do I see the full picture by just looking at the front and the back? No, we still are we want to do that long division process to see what might the y-intercept be if what we have here is in fact a slant asymptote, which at this point we should maybe suspect that that's what we have. Okay, so how do I find my slant asymptote, if it exists? Yeah, we're going to do the long division. We're going to do x minus 1 dividing into 2x squared plus x minus 3. How do I match x to 2x squared? 2x. Subtracting. What is x minus negative 2x? positive 3x. And then how do I match x to 3x? Plus 3. And what do I get for my remainder? 0. What does that tell us? So this it tells us something about the slant asymptote for sure. In particular, what is the error if the remainder is the error between what my function is and what it's trying to be? What is the error between my function and 2x plus 3? There is no error. In fact, my function is 2x plus 3, except when what? Say again? So that would just be the 0 of the numerator, which is okay. Except when x equals 1, which is what we see here in our original denominator here. So before we do the division, before we kind of see this cancellation, what we would see is if we were to factor the numerator, and you could do this from the division, right? We have now this d of x times q of x with a remainder of 0. This is going to be 2x plus 3 times x minus 1 over x minus 1. What's going on at 1? What do we have? We have a hole. We've got that checked 0 here. And so we do not form a slant asymptote. We're not pretending to be a function. We are a function. There is no error between my function that I currently have and something that it's trying to be. It just is 2x plus 3. Except when what? When x equals 1. When x equals 1. And so what is the only thing that I'm missing here for my hole? We just need the y. How do I find the y? Plug in 1 into x. And so what is that y value that we get? I think 5. Yeah. You're good. I did the same thing first period. Questions here with example 3A or B? Yeah, sorry. For B? So if we're looking at 2x plus 3, as x gets really, really, really big, is it going to ever settle down at a particular value? No. Is there any error between it and another function? No. No slant, no horizontal, no any weirdness asymptotes that we need to worry about there. There's just a little hole missing. Yeah. Now, if we had gotten a remainder, then we would have had a slant asymptote at that particular value of 2x plus 3. But because there is no remainder, there isn't a difference between 2x plus 3 and the function we're looking at, except we're not allowed to plug 1 into our function. There would be no vertical asymptote either, because the only 0 of our denominator is 1, and 1 is a checked 0. It is kept in line by the x minus 1 in the numerator. If we had another 0 in the denominator, it would be whatever that 0 is. But because we don't have any others, we're happy to just say we have a hole. It would literally look like if I plug in to my graph, if we say that this is, we'll turn these off. If this is y is equal to 2x squared, we'll do the division here. 2x squared. Plus, what is it, x minus 3, and this is x minus 1, then we very literally do just get a line. Like if we zoom out here, this is just a line. And again, Desmos doesn't really do it justice, but if you were to zoom into what is going on at 1, there would be a little blip right here where we just kind of skip over 1. And you don't see it in this graph because you have to zoom in so like infinitely much in order to actually see that little divot where we jump. And you obviously can't zoom in infinitely much. And so you just never see it on the graph. But like we communicate it with that little open dot there, like what I've drawn on the board. Also no horizontal asymptote. Yeah, horizontal. So when x gets really, 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 really large, our function just goes to infinity. So it doesn't settle down at a particular value. It doesn't approach another function. It's just doing its own thing. It's being itself. And so there is no asymptote there. But that's only because the remainder was 0. If we had seen a remainder, then we would either have a slant asymptote or a horizontal asymptote. Is that a question, Joseph? No. Okay. Other questions here. Good questions. Is that a... Okay. All right. I wanted to... We're going to...